physics from the very largest scale to the very small. I am going to speak about its consequences for elementary quantum mechanics, which turn out to be very interesting and also to reflect upon this question of the meaning of potential fields. The things I'll be telling you are ideas that I developed actually here in Israel about 50 years ago in collaboration with Igal Talmi and with Lindsay Tassi. Well, the 1959 Aharonov-Bohm paper, historically, I can tell you, created a sensation on several levels. On the level of which I'll be speaking, it created a good deal of confusion initially. Many physicists, many good physicists, were really mystified by the notion that the motion of an electron can be influenced by electric and magnetic fields which are confined to regions from which the electron itself is excluded. We were used to the notion that the electromagnetic interaction was itself a local one, local in the Maxwell fields, and the intrinsic non-localities of quantum mechanics did not seem to cover the difference. The confusion was such that there were actually dozens of papers published in good journals claiming either that Aharonov and Bohm were wrong, of course they weren't wrong, they were right, or that we should change quantum mechanics to get rid of this unpleasant phenomenon. Well, you can't change quantum mechanics to get rid of this unpleasant phenomenon without ruining the theory, and we know now that experimentally we don't want to get rid of it because it's there. So, let me remind you, the simplest case, one has a region in which there is a magnetic flux which is confined to the interior of what should be a very long solenoid. Does this mouse? No mouse. Is there a pointer? Oh, mine. There we go. So we have a magnetic field confined to this region. Think of it as a long solenoid. And just to avoid unnecessary arguments about exclusion, the region around it for some radius A is to exclude the electrons. There's an incident beam of electrons over here. They are moving from right to left because this is Israel. They scatter off this structure. Aharonov and Bohm then simply solved the Schrodinger equation, and they found out that the cross-section, that the total scattering, amongst other things, they found out that the total scattering cross-section per unit length of the solenoid is given by this expression. The important thing is, of course, that it depends upon the magnetic flux. Here represented by it depends on it here. Here it's represented by alpha, which is the flux divided by London's unit. Aharonov and Bohm in their paper actually found this result exactly in the limit as A divided by the wavelength goes to 0, but if you do that with finite A, the result is changed only a little, and the main point remains that the scattering does, of course, depend upon the flux. And that was the thing that initially mystified people. Well, I'd like to discuss that in very elementary quantum mechanical terms. If you're going to be realistic, the solenoid has to be finite in length. Let us suppose that the solenoid is millimeters in diameter and kilometers in length. So then there will be some, if the flux goes up through the solenoid, it will come down someplace else, and it won't be on this slide. It'll be off in another country someplace. And so there is a large region here where the experiment actually takes place, a laboratory which could have dimensions of meters around in here, where there is no magnetic flux. If you want to be, you could actually, in principle, shield the flux so that it was literally zero in this region. Well, now, if you look at the Schrodinger equation in cylindrical coordinates, it looks like this. I have written here the Hamiltonian for the Lth partial wave. The canonical angular momentum is quantized in integer units times h cross. The important thing to notice in the Hamiltonian for the radial motion of the Lth partial wave is that the height of the centrifugal barrier does depend upon the flux through alpha, and therefore there's no question that you must have effects of this sort. Because I added a potential V of rho to include the case where you might have bound states, and it's quite clear from this equation that the eigenvalues of the energy in the bound states will depend upon the flux, and also that the scattering phase shifts will depend upon the flux. This quantity L plus alpha, which measures the height of the centrifugal barrier, is, of course, as always in quantum mechanics, simply the kinetic angular momentum R cross mv. But there is something else that's interesting about alpha, which is the following. Here is again the same picture, except that now I pointed out that here is a point R where the electron is at a particular instant. It is excluded from the region where the magnetic flux is, but the electron is the source of an electric field. The electric field is not excluded from the region where the magnetic flux resides. The electric field penetrates here into the flux in the solenoid, probably, and it certainly penetrates into the region where the return flux is, far away, kilometers away, but still it's there. And if you calculate the angular momentum in the crossed fields, the electric field here is the field at the point R prime due to the electron at point R. Here is the external magnetic field at the point R prime. If you calculate that, it turns out just to be equal to alpha in units of h cross. So that's what that contribution to the angular momentum is. Where is it? Well, if you look at that integral, in fact, the contribution from the region inside the solenoid is exactly zero. All of that angular momentum is stored in the return flux kilometers away if the solenoid is kilometers long. There's no question of shielding involved in this. You can shield the electric field so that it does not get into the flux inside the solenoid. In fact, in practice, you really do, because there's a copper wire running around there. But you cannot shield the return flux from this electric field. Gauss's theorem gets in the way. And so this result is completely unchanged by any shielding. So then, so that's what L sub z is. The canonical angular momentum is equal to the kinetic angular momentum plus the electromagnetic angular momentum. And that is the total angular momentum, as a matter of fact, and that's the quantity that's conserved, and that's the quantity that is quantized. So all that hangs together very well. Why were we so surprised by the Aharonov-Bohm effect? It's an obvious consequence of elementary quantum mechanics that we didn't know about. Well, how did the electron get the message that the magnetic field was there in the first place? Well, here's how. The electron could have started far away, kilometers away, past the return flux, where the vector potential is equal to 0, and the canonical angular momentum is the kinetic angular momentum, is equal to an integer value times h cross. Now that electron has to be brought into the laboratory. You have to carry it through that return flux. There is a torque. There's a force on it, and there's a torque about the central axis. And if you calculate that torque on any orbit, you get the same answer, that the amount of angular momentum that you have transferred due to the force on it exerted by the local magnetic field is exactly equal to this quantity alpha times h cross. And that, I think, tells you why the angular momentum is all stored far away in the return flux. But you don't have to do it that way. You could have done it otherwise. The electron could have been placed in the flux-free region in the first place before the magnetic field was turned on. Now when you turn on the magnetic field, there's an induced electric field everywhere, even as far away as Mars, which cannot be shielded out, and you can calculate the torque on the electron due to that, and in the answer you get exactly the same final result as if we had done it the first way. So either way, the shift in the kinetic angular momentum, which is central to one way of looking at this in the nice, simply cylindrically symmetric case, is consistent with the effects not of present local Maxwell fields, but of past local Maxwell fields to which the electron was exposed. So that sounds dandy, but what if the electron was created in the flux-free region by the decay of a neutron after the magnetic field was turned on and had no such experience? Well, of course, no theory is going to work which treats that electron differently in terms of what states it can have than other electrons which got there by other routes. But still, it's a little mystifying to me because I'm not seeing exactly how this electron got the word. Now, you can say that maybe that's something that I should not ask of elementary quantum mechanics. When I create an electron, I have to deal with a field theory that's more complicated. I'm uncertain what to say about that, but consider another case where the issue is much more stark. Consider the electric Aharonov-Bohm effect. This slide I copied from Dr. Tanemura, thank you. And that was Japan, so the electrons are coming in from the left and going to the right. And the idea here is that a wave packet is split coherently as an interferometer. The two parts enter two metal cylinders here, two perfect cylinders. In the idealized case, the two are entirely within the cylinders during a time when a voltage difference is applied between the two cylinders. Now there are electric fields happening all right, but the electrons, in principle, can be completely shielded from them, so they never experience an electric field. And then, of course, there is this interference pattern. and the change in the action, or if you like, the shift in phase between the two waves is proportional to the difference in voltage integrated over the time. And therefore, the interference pattern will be sensitive to this change in the voltage, and therefore to the electric field, which the electron never experienced. Well, how do I explain that to myself in elementary quantum mechanical terms? Well, you can do something. It's pretty interesting. You can express this effect in terms of past local electric fields like this. This equation just follows from the Schrodinger equation, no additional assumptions. The important thing to notice is, if you look in the first term, for instance, that in order to have a phase shift which will be sensitive to those electric fields, there must be a time. There must be a time when the electron is at some point r, where there were in the past non-vanishing electric fields. This integral on t prime only goes from 0 to t. It's the same in the second longer term. So that's interesting. You can only have this Aharonov-Bohm phase shift provided that the electron traverses a place where an electric field was in the past. But now, in the case of this particular, the equation I showed you was for a general multiple connected geometry. In the case of this particular geometry, that place is here in this region, because while the voltage was on, there was an electric field here. The electron just wasn't there yet. Now, so what does that tell me? It tells me that the electric field, that somehow the presence of that electric field in the past did something to all electrons which will pass through there in the future. That is something which I do not understand in any elementary quantum mechanical terms. So that's what the meaning of my title was, about things that I do and don't understand. I can understand it in other terms, of course. If you tell me, well, this shows that this shows that the potentials are real physical things which did act on the electron, and if that is a satisfactory, well, if that satisfies you, that's exactly what it's saying. I think that's what Shira and David Bohm was saying. As you heard from David Gross this morning, it's a tricky business to understand, but this would seem to be one evidence that that is the way you should look at it. Thank you.
My question is as follows. What to do if we use
I can't hear you.
toroid instead of solenoid? In this case, there is no electron flux.
Toroid.
What to do with toroid? If we use, say,
Can you come?
toroid instead of solenoid, and there is no...
Instead of solenoid, what? Toroid. What would happen with a toroid?
Well, okay.
When there is no return
Right,
flux.
that is more complicated. I can show, it has been shown, I have shown, others have shown that you still get this effect. I chose to speak of the cylindrically symmetric situation because it is so simple and easy to understand. if you ask me about in the case that you are speaking of, in fact, there is no electromagnetic, or there doesn't have to be an electromagnetic angular momentum if you shield your toroidal solenoid from the field, but then I'm not accounting for the angular momentum in that case. I guess to summarize what I'm saying, the simple case I can solve exactly and see what's happening, and that tells me what it means for quantum mechanics. I can't. The other case is harder to understand.
Just no. I'm not sure you can shield the solenoid. My feeling that if you shield solenoid from electrons, there will be no effect. Because
no, you cannot be right
if you,
about that.
because you have this imaginary phase, and the reason why I believe it's so, like it was Avi Litzur talk, because we can, in this way, we can find if there is a solenoid or there is no solenoid. You make an experiment, the AB experiment, you see phase, you don't see phase, you find out if there is a flux there inside. And if there is no action at all whatsoever, this is another paradox.
Actually, all experiments have been done with a shielded solenoid because that's how you got the magnetic field. Well, we obviously have to discuss that.
Yeah. You're running out of time here. You're running out of time. But I have a lot of trouble understanding why you have so much trouble with the return flux, because you can have a solenoid, a nice long solenoid, put it in an iron yoke, and have the return flux go through the iron yoke. There's no return flux at infinity. You can let the electron beam go right past the solenoid, and the Aharonov-Bohm effect will not involve that return flux at all.
Well,
so why do you have so much trouble with the return flux?
I don't have trouble with it. The return flux helps me. I chose the cylindrically symmetric case because I could explain why the Aharonov-Bohm effect is inevitable in quantum mechanics.
No, you can have a cylindrically symmetric solenoid inside of an iron yoke.
Yes,
what's the matter with that?
Oh, you can. And if you make that iron yoke cylindrically symmetric, then...
no, I just take the flux off to infinity, Murray, from a top and bottom, and have a soft iron yoke coming all the way around, way away from where the electron beam goes through. I don't see the problem.
What I claim, Sam, is that if I have a soft iron yoke, I will continue to make the thing cylindrically symmetric, which is not infinitely long, but only a mile. Then that angular momentum is in the return flux a mile away.
Well, I would say that you're making a very complicated problem out of a simple problem.
I didn't
experimentally. If you do that.
I didn't speculate it. I calculated it, right?
Well, okay.
Okay, thank you.